an anthraquinone rhodamine sensor. So why study a rhodamine sensor for mercury? Well, rhodamines are kind of special in that they can act as sensors because they have these, you can form these spirolectin rings by a type of chemical closure of the rhodamine. And as you can see, the ring on the left is not particularly conjugated. However, when you add a metal that can open that ring that's been closed chemically and form the traditional open form of rhodamine, which has a really nice pink color and bright orange fluorescence. So if you have these ring-closed rhodamines, they can make spectacular sensors for heavy metals such as mercury. So I synthesized one of these sensors, and today's topic will be a little bit of computational work I've done on this. The computational work was done in VASP. It's primarily DFT calculations, or it is DFT calculations. So on the bottom left, we have a crystal structure, which I got using single crystal XRD. I removed some ambiguity as to the positions so that there's only one position for each ion. So here's the original structure, and then up here are three optimized structure. On the left here, we have just the sensors. As you can see, there's an anthraquinone, and then a ring, and then here's the rhodamine part I was talking about. Here's the ring-closed part I was discussing in the previous slide. And then here's the sensor with just mercury, not mercury 2. And then here's the sensor with mercury 2. As you can see, going from one sensor to the next, there's just not a lot of change. Visually, and the bond lengths don't change substantially either. However, the addition of that mercury 2, but not the mercury, will change the spectroscopic properties significantly. So here's a slide discussing the density states and the binding energy. The binding energy of sensor 1 and mercury is really, really low, almost non-existent, so there's not a lot of interaction. However, when you change the oxidation state of the mercury to mercury 2, as could be expected, that binding energy increases substantially. This is perhaps artificially high. I don't think it's quite that high as far as binding energy, but you can see that there's a significant difference as far as the oxidation state is concerned. You can also see in the density of states here, the sensor 1 and sensor 1 plus mercury are very similar. The only difference is really a peak for the mercury ions, so you're more or less just putting two things in the same system. They're not really significantly influencing each other. However, when you add mercury 2, there's a substantial change in the density of states. The band gap changes, so you just have different orbitals you're considering when you add the mercury 2. So looking at the theoretical absorbance spectra, you have sensor 1 and sensor 1 with mercury 2. This is kind of neat because, as you can see, in the sensor 1 plus mercury 2, you get the addition of a peak in the 5 to 600 range, or maybe 2 peaks. This correlates very well, actually quite well, with the experimental data, which is down here, where you have your sensor 1 here, and then your sensor 1 with mercury. So again, you see a peak in the 5 to 600 range. So this just shows that the computational data matches pretty well with the experimental data. Another thing I investigated was energy transfer between the quinone and the rhodamine in a FRET type of process. You typically have two fluorophores. When you excite the one, if it's of similar energy to the other one, you can get energy transfer so that the second fluorophore is excited. So traditionally, the anthraquinone is considered the acceptor and the rhodamine is the donor. And you can see I can take two sets of excitations, two transitions, that is, for sensor 1 and then the sensor 1 with mercury, and use those to find the energy transfer, the rate of energy transfer, more or less, which is proportional to the square of the FRET coupling constant. So I calculated using those orbitals that I showed you on the previous slide, the FRET coupling constant, and then I squared that, and you can see that the energy transfer rate is going to be much higher for when you have the mercury than when you don't have the mercury. The reason for that is, going back to this previous slide, the orbitals on the rhodamine for when you have the mercury are much closer than when you don't have the mercury. So this FRET coupling constant is 1 over the cubed root, the cube of the distance. So you'd expect it to be much lower for a longer distance, right? And I have have a very, very brief video of molecular dynamics. Very brief. Okay. Thank you.
Okay, thanks, Mariah. Thanks.